Everyone, today we will talk about the area in polar coordinates. Specifically, we will talk about the area bounded by a polar curve, which is, in this case, the easier of the two areas we are going to talk about in our polar coordinate system. So, what's the big idea behind the area bounded by a polar curve? Okay, as you can see, our polar coordinate system is like a big circle with different radius or radii that we can use to plot our polar curve. So let's say if we are to take the area, let's say we have to take the area of a circle like this one, but we are only tasked to take the area from here to here, wherein we are given radius r. We can use the formula for it's just like taking the area of a sector, because this area is a sector of the circle. Then the area of a sector is just equal to 1/2 r squared times theta, wherein our theta is in radian. Okay, so let's say this one, we have to take the area of this sector. We are just only given r and our theta, wherein it started at 15 degrees or pi over 12 and it stopped at 5 pi over 12. So to take the area of that sector, we just have to take 1/2 times r squared. R is a constant. Then to take the theta, we just have to get the difference from the bigger angle to minus the lower angle. So 5 pi over 12 minus pi over 12. Why? Because we are only finding the area from 5 pi over 12 to pi over 12, or vice versa. To be mathematically correct, we have to subtract the bigger angle minus the lower angle because we don't have a negative area. Okay, so this is just the area of the sector is just equal to 1/2 r squared times 4 pi over 12, or simplifying, that is, we have 2 and 1 over 6. So this is r squared over pi r squared over 6. Okay, now you get the idea of getting the area of a sector using the polar coordinate system. Let's say this is our beta and this is our alpha. Okay, now we have a certain problem wherein our curve is not always a circle. Our polar curve is not always a circle. We have our limason, we have our chordoid, we have our rose, and so on and so forth. So what if we have a curve wherein the radius is not always equal to some number? What if we have varying radius at any given point? One way to solve for that is to approximate, okay? We have to approximate the area of the curve by we can only do that by using the area of a sector. Let's say this is our sector. Let's say this is our sector. It's only an approximation because we have a leftover area over here, okay? But if we transform our angle into a very small angle, let's say let's denote that as delta theta. If we make that very, very small, our approximation just becomes accurate. It becomes more accurate because we will now just be having a very small area of a sector. Let's say that is very close to a single line. Now, if we add these small sectors at any point of the circle, at any radius of the polar curve, we now can approximate the area of the polar curve. So the area of the polar curve can be represented as 1/2. Let's say we have R1 over here, then we have R2 and R3 and so on and so forth, and our theta is delta theta. So our delta theta is constant at any given radius. The only difference is the radius that we are given, plus 1/2 R2 squared, we have squared delta theta, plus 1/2 R3 squared times delta theta, plus and so on and so forth. Then as you can see, this is just a summation. Now we can represent this one using our sigma notation. So the area of our circle is just equal to 1/2 times r sub n squared times delta theta from let's say that is r sub I squared summation of 1/2 r sub I squared times delta theta from I is equal to 1 to I is equal to n, wherein our n is the number of radius or the number of different radius that we have in the polar curve. Now, to make that more accurate, as I said before, we have to make our delta theta smaller. Okay? So, to do that, we have to take the limit of this area as delta theta approaches 0. So, our area of the curve is just equal to the limit as delta theta approaches 0 of the summation of I is equal to 1 of the summation of 1/2 r sub I squared delta theta from I is equal to 1 to I is equal to n. And by the fundamental theorem of calculus, we now know that the area of the curve is just equal to a definite integral of 1/2 r squared d theta from alpha to beta, wherein our r is a differentiable function of theta, or is an r of theta or f of theta. Okay, our alpha and beta is our upper limit and lower limit. It's just like what we have done earlier, wherein where we start and where we stop in finding the area of the polar curve. Now, in summary, the area of a polar curve is just equal to the integral of 1/2 r squared d theta from alpha to beta. That is our general formula for area bounded by polar curves. Now, if you somehow forgot our general formula, just think about the area of a sector. It's almost the same. Our theta is just replaced by d theta, and now we only have the integral in which we have our upper limit and lower limits. It is all derived from the area of a sector. That is the big idea behind the area bounded by a polar curve. Hope you learned something, and thank you for listening.